Hello everybody, my name is Jacob Videra and this is the foundation design final project for bridge number 03641 in Milford, Connecticut. Why did I choose this bridge? Well, I chose this bridge because it is the bridge for my senior design project, so I actually already had a head start on all the technical stuff and I've been working on this bridge for a while, so doing the foundation wouldn't have been that out of the way for exactly what I was doing anyways. Also, this bridge is a very simple foundation. The foundation is just a simple one column foundation with a square foundation right underneath. The bridge in and of itself is a bridge that runs over Naugatuck Avenue in Milford, Connecticut over the Metro North Railroad. It consists of two spans, both running about 99 feet together, but the one span that we're working on, span 1, the one that you can see in the image in the bottom right hand corner, only spans about 67 feet and 10 inches. Also on this slide, you can see the elevation of the bridge. It goes down about 57 feet, up from where the top of the bridge is to the bottom. And next up, we can see the program I used for this project. I used SP Slab to calculate the deck, which would be the ultimate applied load over the entire bridge. The SP Slab documentation right here helped me get all the values that I needed later on for the foundation design and the bearing capacity, as well as all the numbers I needed to calculate the applied load over the bridge that we will see in just a second. Here we see the applied load over the bridge. We see down there that the applied load over the entire bridge is a pretty large number because it actually is a pretty long bridge. But in individual sections, the applied load is not that crazy in comparison to other bridges that are around the same size for it. Up top, we can see the dimensions of the bridge. I rounded span 1 of the bridge to 68 feet because it was 67 feet and 10 inches, and 68 feet is a very nice square number to do the rest of my calculations on. The depth of the bridge is about 17 feet and 11 inches. That's from the top of the span to the bottom of the bridge. And the pure dimensions, it is 14 feet, 14.583 feet by 14.583 feet by 17.11 feet. So that's the dimensions, length, the width, and then the height of the pier. And that is where our base will be. You can also see the dimensions of the wing walls, but those are less important for this presentation. It's just to give you a visual of what the bridge will look like. For the two flood conditions for the bridge in and of itself is actually pretty hard to flood. The reasoning for that is because at the bottom of the bridge, it is right over the railroad tracks, is a gravel base. So most of the water from the pier that is right next to the bridge, if it ever did flood, would just go right into the base and get compacted down to the soil and get compacted down to the gravel and whatever soil is right underneath. So it would most likely just become groundwater. And any other flooding situation over the top of the bridge would fall into either catch basin, since the bridge in and of itself is shaped like this, to sort of encourage the flooding to move outwards, not sit on top of the bridge. So there wasn't a lot for me to do for the flood conditions except to explain that they are not very likely to happen. And yeah, on the next slide we can see boring log 1. For both of the boring logs, I'll explain in this log, but for both of the boring logs, there were some assumptions that had to be made. It was hard for me to get information on the soil underneath the bridge, since the Connecticut DOT built this bridge about 30 years ago. So all the information on what is going on underneath the bridge is not published. 30 years ago, they didn't keep the same records as they do now, so I don't have any records on when they actually did the boring for this bridge. So the assumption was made that the top layer of the bridge is definitely gravel, and because this was the boring log for clay and silt, I assumed that the underlayings of the bridge were clay mixed with some sort of gravel. Not a lot of, and the gravel decreases in value as the elevation goes down. You can also see the information, the description of the material on the right-hand side there. Most of it's the same, but is basically just to describe how the gravel decreases the farther down into the elevation that you go. And you can also see the elevation chart right here to the right of it. Here in boring log 2, we can see a similar situation, but this time with sand. So the lower you go down, you can see that more gravel starts disappearing and more sand starts emerging. but sand is fine grained, so it'd actually be better if during boring they use sand. That way, all the material would sink down to the bottom or get absorbed by the sand and not stay on the surface or the flood if it were to flood. Here we can see the foundation design. For the foundation design, I used the formulas found in the slides for this. We did 2 foundation designs, one for shallow and one for deep. For the rest of this, I will be using the shallow foundation design because of Metro-North Rail Line. They actually prefer a shallow foundation over a deep one to keep stability over the railroad tracks. They don't want the railroad tracks to run over a foundation. They'd rather run over just a simple gravel and sand and compacted soil underneath it. So here we can see the D for the shallow is 5 feet and H is 9 feet. And for the deep is 30 feet and 38 feet. And we can also see the QU for the shallow is 9.47 pounds per square feet, and the QU for deep is again 9.47 pounds per square feet. The QU actually doesn't change between both. None of the values change between the both of them. And here we can see the bearing capacity calculations. For the bearing capacity calculations, we assume that the foundation is supported by soil with a rigid base at a shallow depth, as it is built over railroad tracks, and the deeper base would not be approved by Metro-North, like I just explained before. I got all of my N values from table 6.1 that you can see on the right. I didn't have to use any F values because of the bearing capacity formula that is used for this kind of foundation. So my total Q net is about 2,020 pounds per square feet, and my QU here is about 6,061 pounds per square feet. Here for my settlement, we can see that my SGE is 1.16 pounds times feet, as it is usually denoted. And also, since the bridge is over gravel, we are using the settlement formula, and you can see the formula listed right there. I'm not going to say it out loud because it is just a bunch of numbers and symbols. For the consolidation settlement, we will be using this stress formula. The total stress that we got was 0.99 pounds, which is actually pretty good for the bridge. It should be low stress. And in conclusion, the bridge has a high applied load. The bridge should use a shallow foundation. The bridge has a high total bearing capacity due to the weight of the entire bridge on the one pier, and the bridge has low stress and a good settlement value. Thank you.